will start. Uh, Good afternoon, everyone. Welcome you all to our first colloquium on SNBO's colloquium series on quantum materials and devices. Now I'll request our director, Professor Tanusri Saha Dasgupta, to introduce the speaker and also chair the colloquium. Thank you very much.
Thank you, Manoranjan. So let me just start saying a little bit about this series. So in SNBO Center, we have, it's a small institute, but even within this small institute, we have a very good fraction of people who are interested and working in the area of quantum materials and devices. So we thought it will be pertinent to start a series on this. And this series has been basically coordinated by Professor Manoranjan Kumar and also Nitesh Kumar, one of them being theoretician and one being experimentalist. And this is the first talk in this series. And I'm extremely happy that really illustrious scientist like Professor Bob Cava is the first speaker of this series. Nothing can be a better start than this. Having said that, many of you know Professor Cava. Some of you, especially the young people, may not know. So Professor Cava is one of the leading and, in my opinion, perhaps one of the best solid-state chemists of my time that I know of. And he is currently the Russell Wellman Moore Professor of Chemistry at Princeton University. As I already said, he is a solid-state chemist, and I really liked his abstract, which is kind of provocating. But people like us who are materials physicists, they rely a lot from the collaboration from solid-state chemist friends. So he has therefore major contribution, and the contribution he has made in the fields are actually domain of this condensed matter physicists. Superconductors, frustrated magnets, topological insulator, thermoelectrics. So you can already see how much is the influence of quote unquote the solid state chemist in this area, which you would think primarily is that of the physicists. So physicists do benefit a lot. I mean, without really the help and the strong active collaboration from solid state chemists, it would have been impossible for the materials physicists to make any mark in any of this area. And as I said, I found the abstract by Professor Cava very intriguing. In the sense, he said that some of you might find it interesting, some of you may not, but we already find the number of attendees at the moment has reached, it has crossed 100, it's 124. And this institute primarily is the Institute of Physics. So you can already see there's so much of interest about your talk among the physicists. So with that, without spending much more time, I would really welcome Professor Cava to deliver his talk, and I am very eagerly looking forward to his talk.
Thank you. Okay. Everybody can hear me? It's just a little confusing to me, but I got it. Okay, so solid state chemistry is a wonderful field, and I have to say India is well known for its excellent solid state chemistry. So it's a pleasure for me to speak with you. Over my career, I've become involved with finding materials that have interesting physical properties, and that's because that's the way I look at the world. I want to try to invent things that do that, and that have properties, and we'll see the results that have been obtained by these nice graduate students whose pictures you see at the bottom. Here they're all gone now, moved on to in their lives, but they have done beautiful work, I think, and I'm happy that you could see the two funding agencies that have been willing to pay for this over time. So let's see what next. So first we'll talk about geometrically frustrated magnets. So if the normal case for metals with unpaired electrons on lattices is that at some temperature you get antiferromagnetic or ferromagnetic ordering. And you can actually mess with this ordering by solid-state chemistry, using solid-state chemistry to put the spins on different lattice types. And the two most famous frustrated lattice types are triangular lattices and tetrahedron. And the thing is, it just illustrated, there's a way to get a pointer, right? I'll find it. Yeah, this way. So this one is a simple triangle, and you can see if you have antiferromagnetic coupling between spins, the third vertex doesn't know which one to line up antiferromagnetically with. This is kind of a trivial way of looking at this. If you have a tetrahedron, then these two vertices don't know how to line up. And so when you have triangular lattices, you get spins summing to some zero moment over a larger number of spins. And when you do that, there's a larger number of degenerate states possible. So you end up with many possible low energy states, which results in, let's say, magnetic frustration. So we can tell how frustrating a lattice type is by looking at the ratio of the Curie-Weiss theta, which is a measure of the average interaction energy between these spins and the actual ordering temperature. And there are some pictures of lattices that are well known to have this property. Here's a Kagame basket, which is made up of corner sharing triangles. This is a very frustrating geometry if you can put spins on that lattice. And here's the pyrochlor lattice, which is just corner sharing tetrahedra. So what is the 2D and the 3D version of the same kind of frustrating system? Okay, so aside from the poisonous and radioactive elements on the periodic table, you can use many of these elements in compounds to try and get a particular magnetic or electronic state. And I'm sorry that there are so many things circled here, but we're going to look at this. We're going to take things that are electropositive, meaning they always donate the same number of electrons in a chemical substance, except under extremely rare circumstances. The transition metal series, which are these yellow ones where we can control more or less the number of electrons that are left in the d orbitals. And then so antimony, which is our magic element, and then oxygen and fluorine, which always accept electrons. And then this is the rare earth series down here. You change the number of F electrons that are in the F orbitals. And you all know from early chemistry classes and physics classes that F electrons are close to the nucleus, so their interactions with each other are weak. Okay, so it's fair to ask, with those two lattice types that are the best known frustrating lattices, which one is more frustrating? Which is worse, a 2D system or a 3D system? And this, coming to understand this, how to figure this out, was a two-step process that first involved understanding that the pyrochlor lattice, that pyrochlor materials, which have the formula A2B2O7, are typically have two interpenetrating sublattices of corner-sharing tetrahedra. So when you look at the crystal structure of where the metals are in a pyrochlor, you can easily see that you can, not so easily see, that you can separate the crystal structure into two sublattices. And they both have corner-sharing tetrahedra. And then the other realization is that you can take that same array of lattice points and distribute different kinds of atoms on them, in which case you can separate the magnetic lattice from the next plane of magnetic elements by putting non-magnetic elements in between. So now we can take this lattice type, this pyrochlor, and for certain circumstances only, put non-magnetic atoms on some of the lattice sites to make the material go directly from a pyrochlor to a Kagame net. So this red net is a Kagame layer. So I think the next slide is the relevant one. In solid state chemistry, we typically draw crystal structures this way, which show the metal oxygen polyhedra. And this is this material that this graduate student found, rare earth 3, antimony 3, magnesium 2O14. And this was a known substance before, but it had been looked at this way, which shows the metal oxygen polyhedra, which is how it's a good way to think of this if you're a solid state chemist. But if you're interested in the magnetism, the thing to do is to take all the confusion out of the picture and just reduce it to just the magnetic sublattice. And then you can see that if you could make this with the same rare earths, you can make an A2B207 pyrochlor and make a A2SB3MG2O14 Kagame. And if you just look at the magnetic sites, you can clearly see that this one is a pyrochlor made of corner sharing tetrahedra. Here's 2 of them. And this one is a Kagame. Okay. So the trick is always to see the forest through the trees. Let's see, can we get the next slide? Okay. So now we can take if you can make this with different kinds of rare earths, if you can make the equivalent pyrochlor and the equivalent Kagame with the same rare earth, then you can do a test, and you can actually test whether the Kagame is more or less frustrating than the pyrochlor lattice. And that's what we did. And you can do it with neodymium only. Well, neodymium is one of the few rare earths that you can do this with. And you can see this is the temperature dependence of the magnetic susceptibility and the temperature dependence of the inverse magnetic susceptibility versus temperature. They almost are no different. So basically from a large scale view, the Kagame and the pyrochlor are extremely similar. And even though, and the Curie status are ridiculously low, which will get us to the next part of the talk. But the magnetic moments are similar. The Curie status, which is a measure of the interactions, are really, really low. Eventually, these materials order at low temperature, and you can see that in our world by looking at the heat capacity as a function of temperature. You can see that the Kagame orders at this peak is the loss of entropy where you have magnetic ordering, so it shows up in the heat capacity. And so the Kagame orders at a slightly higher temperature than the pyrochlor, so the 3D system is more frustrating. The thing I want you to notice about this is there's some really low temperatures involved here. This is like a half a Kelvin, and this is like 0.3 Kelvin. So these things are really low. And this has to do with the fact that the rare earths, the elements, the electrons that are unpaired in the rare earths are in the f orbitals. And those f orbitals are very close to the nucleus. They have a high angular momentum. They are just not very strongly interacting with each other. So even though you can get magnetic ordering these things, you need special equipment to get to such low temperature. So this field of looking at rare earth pyrochlors has been active for many years, and there are many interesting people working on it. And 3 of the people who I like are these 3 theorists, Michel Gingras, Leon Balance, and Roderick Mosner. And independently, as I was back in when the world used to be possible to wander around in it, these 3 people asked me independently, fine, magnetic pyrochlors are fun, but can't you do something that makes the magnetic interactions larger than 1 Kelvin? So, we want to be able to measure something. And that's always a trick in the world. You have to be able to measure it. Well, you don't have to, but it would be best if you can measure what's happening. Okay, so it may have taken me 10 years to figure out how to do this, but eventually we did it. And it has to do with asking what are the requirements for the materials that you would need to make the magnetic interactions higher than 1 Kelvin so people could study them. Well, the magnetic transition elements, which are 3D elements, are much more strongly magnetic than the rare earths. You know that 3D elements like cobalt and iron and nickel make magnets that stick to your refrigerator. So magnetic ordering can happen at much higher temperature. And the typically highest magnetic moments are what you get with 3D transition elements, meaning the 3D series of transition elements, where the unpaired electrons are in 3D orbitals, so they're not hybridized too much with their ligands, and they need 2+ transition elements to give you strong magnetism. But there's a problem with that. There are two problems with it. First of all, we have to put them on the B site in the pyrochlore, which we realize is also geometrically frustrated. And so we have to have non-magnetic atoms on the A site. We have to have divalent atoms on the B site. And we have to have the right amount of charge so that they become charge balanced. So you therefore have to make these things with fluorides, not oxides. So we're able to figure out that by making A prime B2 F7, we can make rare earth pyrochlores that were magnetic and had a higher interaction temperature. And these were grown in a floating zone furnace by my student Jason. And they are insulating pyrochlores with these two sites disordered on the A sublattice and the magnetic atoms being divalent transition metals. We'll see that this disorder probably has something to do with it. You can grow gigantic crystals of these in a floating zone furnace, so they're suitable for neutron diffraction. Here is how beautifully I like this plot because it's a beautiful plot of the 1/chi behavior, 1 over the susceptibility behavior of neodymium calcium CO2 F7, which is now a pyrochlore. The slope of this line tells you the magnetic moment of the element that's in it, of the magnetic element, and the intercept, the temperature intercept, tells you something about the strength of the magnetic interaction. And now you can see that the intercepts are large. Here's a table that shows these things for the cobalt and nickel ones. The intercepts are large. The effective moments are large. The intercepts are large, but they don't magnetically order near this transition temperature. And that is a symbol or signal that they're magnetically frustrated. So actually, the really great news here is that we did it. So these things now have magnetic ordering temperatures of hundreds of Kelvin instead of fractions of a Kelvin. And they have beautiful Curie-Weiss laws, and they're beautiful insulators. So look at this one over here, this nickel one. Nickel is spin 1. So here you have spin 1 on a pyrochlore. Cobalt is really bizarre and wonderful, so we'll see more about cobalt later. But now what happened? So when you go all the way down here to around 2 or 3 Kelvin, they finally magnetically order. And what is that? Now, I am pretty sure that if we didn't have to get charge balance by mixing these atoms on the A site, like sodium and strontium, which are different from each other, they induce a kind of weak disorder into the system. They're not on the magnetic lattice. They are bonded to oxygen or fluorines that are in turn bonded to the magnetic atoms. And that gives rise to some kind of disorder in the system that's weak. And they become spin glasses at low temperature. And there are classic signatures, experimental signatures for spin glasses. And so I think that these materials would be like the world's most perfectly frustrated magnets if we could figure out some way to get rid of this disorder. And the materials physicists who we work with have been bugging me for like 10 years now to figure out how the heck to do that. I can't imagine how to do it because I need this site to add to 3, or I need to put some oxygen on the fluorine sites here, or do something to make this go away, but I can't make it go away. Anyway, they're spin glasses. That's been going on for years, and those materials are presently being actively studied especially by neutron scatterers, because we can make such big crystals. I think making crystals of things is really, really important. So obviously having the idea for what to do is really, really important. But then from a materials perspective, being able to make something that does it is where solid state chemists come into the picture. And it doesn't turn out to be too easy a lot of the times. So I think that right now we have quantum spin liquids, which fits right into your quantum aspirations. And I think that the first one that I know that was illustrated to do that. The first material was sodium 2IRO3, which is like Na3NaIr2O6, which is a honeycomb lattice of iridium, and iridium 4+, which this is based on, has one unpaired electron. So if you put that here and here, if we extract now the magnetic lattice from this crystal structure, this magnetic lattice has a honeycomb. And a honeycomb lattice, you can see right here, every uncolored ball is surrounded by 3 balls of the opposite color. And so you can actually write down a model for how magnetic interactions could happen on such a lattice to yield a state at low temperature where you just have entanglement of spin-1/2 particles on this lattice, if you can actually find a material that does that. And although sodium 2IRO3 was the first one that was found, it's not possible to grow big crystals of this material because iridium is not soluble in anything. I know that somebody has reported crystals of Na2IRO3. I am certain that their material blew up, that their crucible exploded or something in their furnace, and when they took it out, they found crystals in it. They have no idea how to do it twice. Alternately, ruthenium trichloride has a honeycomb lattice. This was, I thought, a brilliant observation by these people at Oak Ridge, that you can grow crystals of ruthenium trichloride, which has a honeycomb lattice of ruthenium with nothing in a hole, and the ruthenium is bonded to chlorine. Now, the wonderful part about this is that it's chlorine, not oxygen, and it's ruthenium, which is a 4D element, not a 5D element. So iridium is a 5D element. Sorry, 5D element would be something from the bottom of the periodic table, where the unpaired electrons are in 5D orbitals. In ruthenium trichloride, the unpaired electrons are in 4D orbitals, so they're closer to the nucleus. We learned early in our careers that as you go to lighter and lighter elements, the effect of spin-orbit coupling is weaker. And in this kind of honeycomb, this theoretical model for honeycomb lattice, you have to have strong spin-orbit coupling. So what these people did was, instead of using a 5D element where the spin-orbit coupling was obviously going to be high, they used a 4D element where the spin-orbit coupling was not obviously high, and it worked anyway. The good news is that if you take that material in low fields, it spontaneously makes an antiferromagnet, and we'll see a picture of that in a minute. But as you apply a magnetic field to it, you change the ratio of interactions that are present in this honeycomb. You change the interactions to each other, and at around 10 Tesla, which is almost too high, but not quite, you can get this kind of bizarre magnetic state, which is called a Kitaev spin liquid. So that's the quantum spin liquid state. So the quantum spin liquid state shows up at around 10 Tesla in ruthenium trichloride. So that's the basis of this whole thing. And yeah, so people started this Kalyunin is a person who has a lot to do with my research after this. So if you look on a honeycomb, if you just don't worry about, what sophisticated electronic models or magnetic models for honeycombs, it was already known that there were 4 types of magnetic ordering in honeycomb lattices at low temperature. One is typically called Néel ordering, where you have neighboring, each spin has a neighbor with the opposite spin configuration. Then you can have stripy, where you might have two that are ferromagnetically coupled and that are antiferromagnetically coupled to the next 2. You can have all ferromagnetic, you can have zigzag. And the theorists realized at some point that if you change the ratio of near neighbor to second nearest neighbor interactions, you can switch between these states, the Néel state, what's called stripy state, ferromagnetic state, and zigzag state, by changing the ratio of the magnetic interactions. And this chart right here motivated a lot of our work subsequently, because we were looking, because on this chart, there are two regions where we expect to find a quantum spin liquid. So we began looking for quantum spin liquids in these two regions, and you can try to adjust that yourself, or you can hope that nature gives you a material that does that. And yeah. So before the theory started coming out, and this was in April 2002, I realized that these materials had honeycombs, materials A, nickel 2 or cobalt 2, P2O8 or VO42, something like that, where they're mixtures of a big atom and then transition metal atoms and then plus other atoms in tetrahedra could make a honeycomb lattice. And that honeycomb lattices are intrinsically interesting. And that, for example, barium nickel 2 V2O8 is an example of something with a spin 1 honeycomb. For the theorists in the audience, they remember spin 1 honeycombs are important systems for topological physics. So we were looking for spin 1 honeycombs back in the day. Found that barium nickel vanadate was one of them, and it eventually magnetically orders. You know, it matters a lot. I mean, I'm sorry that the world changed. I hope it goes back, but it matters a lot to just talk to people informally. And this theorist, Kalyunin, stopped me on the way to a cafeteria one time and said, well, what about cobalt? And cobalt is a bizarre element in the periodic table. So it's a 3D element, so it should have only spin contribution to the effect of magnetic moment. But in every single compound that is known with cobalt, as far as I know, the moment is too big. So there has to be, no matter how you count the unpaired electrons on cobalt, whether it's high spin or low spin cobalt, you have to have a significant orbital contribution to the magnetic moment, which means that there has to be spin orbit coupling in the system. So cobalt is a brilliant observation by this theorist. So what about BaCO2P2O8 or BaCO2P042, depending on how you write the formula? Why not? Why not try to tune that one to see if you can get to this quantum spin liquid? Well, it doesn't work. And the reason it doesn't work, we tried it by changing the thing on the tetrahedron. And the tetrahedron is off the magnetic site, so you expect something that it's okay to do chemical substitutions on that site, but it doesn't work because of this weak off-site disorder. So that didn't work. But I was not deterred from this idea, and so now we tried to grow BaCO2P2O8 by itself, and in a flux, we got a new compound which is based on a cobalt triangular lattice. Now, you know from what I showed you in the very first slide that triangular lattices are interesting too, planar triangular lattices. This is cobalt 2+ on a triangular lattice, and it can be grown as crystals. So, as I probably told you in the beginning, you know, you can have all the wonderful ideas you want, but a field really gets legs if experimental physicists can get materials on which to do experiments and explore new kinds of physics that might happen, or new understanding for physics that's been observed in the past. So the good news is that this can be grown as big crystals. It's a triangular lattice of cobalt. Here's the young lady who grew it. Here's our PhD advisor, John Tranquata, who I have to give a lot of credit to because I gave him a lot of grief in his life, and he's stuck to it. The good news about sodium 2 barium cobalt P2O8 is that it never freezes. So you can go down to like 50 millikelvin, and there's never any sign of a magnetic ordering transition. So you have a cobalt 2+, which is a spin and a half on triangular lattice that never freezes, and only when you put it in a magnetic field on the order of a few Tesla do you see something in the heat capacity that indicates that the spins actually freeze. Now, this substance has now been out for a year or so, a lot of people have seen the data, and nobody has objected to it. You know, I'm a kind of person where, you know, it's like tossing something out in the world, or not tossing, doing enough to try to convince people that a material is interesting, and then who knows what happens after that, and experts need to take a look. This one has been objected to. The most funny objection I got to this material was too many elements: sodium, barium, cobalt, phosphate. So for a solid state chemist, this is not a ridiculous number of elements, but this illustrates something. If you invent a new material, even if it has interesting physical properties, you have to be able to grow crystals of it, and the crystal structure and the material has to not be too complicated for people to work on. Which led us, so I'm not easily deterred. So this led us to barium cobalt As2O8. Now this material came about in the 1970s, and it was studied in the past. It has a honeycomb lattice of cobalt, and under zero field, it magnetically orders. So here is the temperature-dependent magnetic susceptibility of barium cobalt arsenate. It can be grown as single crystals. So here's a single crystal of barium cobalt arsenate. It has a layered honeycomb lattice of cobalt atoms. And you could ignore this and say, okay, it's not interesting. Or you can learn from ruthenium trichloride and put a magnetic field on it and see what happens. Well, something crazy happens in a magnetic field. Not only, and the first order look at something as a magnetic field would be to look at the M versus H loop, the magnetization of the sample versus applied magnetic field. And the thing about barium cobalt arsenate is that it has multiple steps in its M versus H curve, which indicate that there are multiple magnetic phases present. So it undergoes, in a field of a fraction of a Tesla, it undergoes a phase transition to something else. And by 0.4 Tesla, it really undergoes, it's in the third magnetic phase altogether. So who knows what's going on here? For me, the clue that there was something really wacky happening here, it has to do with the fact, with the thermal conductivity. And this is not a normal measurement that people make, but I have a collaborator in physics who does this kind of work a lot. His name is Pon Ong. And we gave him crystals of this barium cobalt arsenate, and his students figured out that if you look at this material in zero field, it conducts heat by the transfer of phonons and magnetic excitations. But when you apply a small magnetic field, the thermal conductivity suddenly drops rather dramatically. And as it drops dramatically, that means that you no longer have well-defined magnetic excitations. So these magnetic excitations no longer carry heat. And so this is an indication that there's some kind of bizarre magnetic state happening at about half a Tesla. And so you can make a phase diagram, which is something that we're good at, where you put this cobalt-based honeycomb lattice in an applied magnetic field of only a half a Tesla, which is 5,000 Orstads, and you end up in what we think is a Kitaev quantum spin liquid state. And now, I mean, lots of people are working on this now. So good news. The really good news is the theorists stopped me on the way and said, what about cobalt-based honeycombs? We made one. It just, by some miracle, it falls at some point where almost the Kitaev terms are almost the same size as the normal antiferromagnetic terms. And so it shows this quantum spin liquid state in a very small applied field. Okay. Now, I think, yeah, I can't tell what time it is. So I know I'm talking too much, but basically, right, I still have some time. So now we're going to talk about something that has a purely chemical question at the bottom of it. And that has to do with the element gold. Gold is a bizarre element in the periodic table that almost nobody has noticed. And the good thing about gold for human beings is that for the history of time, gold has been considered an inert element. So gold zero, gold metal, does not form a native oxide or a native anything easily. It just doesn't react with much. So you can make beautiful gold objects. I know that India has a lot of this old metal working where people figured out how to make objects out of gold and gold alloys. And gold is really famous for being what's called a noble metal, meaning that it's normally uncharged. It stays an element. But the position of gold in the periodic table is right here. So here's a little excerpt of the periodic table in the vicinity of gold. So in the 3D series, we have cobalt, nickel, copper, and zinc. This is D10. This is, well, D8S1. This is D8S0. This is D7S2. God knows what these things are as metals. But the important point is that when you put these things in a chemical substance, this column here, nickel, palladium, and platinum, make something that where the S electrons go into the D states and create a filled D orbital, which then, once an orbital is filled, it drops in energy. So these things when you count the electrons in intermetallics, these things count as 0 electrons. Copper, silver, gold counts as 1 electron, single electron donor. These count as double electron donors. So you expect gold plus 1, copper plus 1, silver plus 1, gold plus 1. So, and a perfect example of that is yttrium, gold, antimony, which is a semiconductor. But there's a catch. So far, so good. We expect gold to be gold 0 if it's just in a metal by itself or alloyed with other metals. But if you put it in combination with something, expect it to be plus 1. But if you look at the electronegativity, which is the tendency of an atom to accept electrons, you can see that platinum and gold want to accept an electron as much or more than sulfur, selenium, and tellurium. What? So that means you can make a gold minus. So, if gold accepts an electron, then we can get gold in a bizarre oxidation state where you have too many electrons on the gold. And all you need to do, well, not all you need to do, is to put gold in combination with some element that really wants to donate an electron, and you might get gold to accept the electron. Okay. So part of my interest in the world has to do with confusing elements. So you take an element and you take what it wants to do normally, and then you put it in some kind of crystal structure that makes it not do what it wants to do. And so we made gold, lanthanum, antimony in a 1:1:1 ratio and asked what happens. And it turns out, well, we're lucky, but this was a directed luck, that something interesting happened. And that is, instead of the crystal structure that you normally see, let me go to the next slide. Normally, when you make these 1:1:1 compounds in this part of the periodic table, you get hexagonal materials where you get the gold to be in a tetrahedron where it's bonded, where it just clearly donates 1 electron to the neighboring atom, which in this case is a tin. So lanthanum gold tin has the gold bonded to a tin. And you can count the electrons in lanthanum gold tin and have it be a normal valence compound. Lanthanum donates 3, gold donates 1, tin accepts 4. So that's all good. We get an 18 electron thing, and 18 electron rules in solid state chemistry are like an 8 electron rule in organic chemistry. Organic chemistry, it follows this rule all the time. Solid state chemistry, it's more like a guideline than a rule. Sometimes it works, sometimes it doesn't. When we went from lanthanum gold tin to lanthanum gold antimony, now we have antimony has 1 more electron than tin. So now we have 19 electrons per formula unit, not 18. So now we're going to disobey the 18 electron rule. What happens? Do you make a compound at all? Well, you do. And when you do, you get some bizarre event, which is that this layers shift relative to each other to put the golds next to each other. And when the golds get next to each other, the golds actually form a bond. So you get a gold-gold bond between gold zeros in this crystal structure. And you get what's called orophilic bonding, which turns out to be making a bond between inert atoms is very bizarre in chemistry, and we finally got one. And this was my first JAX paper. I like to tell my students that our shortest period of time for a solid state chemistry paper to be rejected from the journal JAX, which is Journal of the American Chemical Society, is 1.5 hours. So the chemists really hate, they hate solid state chemistry, but we're making a little progress there. But, anyway, that's the end of that story. Okay, so now we're going to move on. The last time in the periodic table. I think I have a few more minutes, right? So now we're going to ask another chemical question that actually has a relevance to physics a lot. This has to do with spin. So spin again, you want to our ultimate goal is to make aside from the gold thing where we're just asking where are the electrons, we want to make a spin system that gets to low temperature and never orders. So it makes a quantum spin liquid, or a spin liquid at low temperature where there's no magnetic orderings of the spins. And we already learned that hexagonal or triangular motifs are good for getting spin systems to not order down to low temperature. And this is a set of materials now that I realized was interesting for a bizarre reason. And there are a lot of these things, and I don't hear people talking about this particular aspect of them much, which is that barium 2+, which is shown here in gray, is about the same size as an oxygen 2-. So we all learned early in our lives that closest packed lattices are very, very stable because the balls are all touching like this. So it's a beautiful, you can stack oranges or grapefruits or whatever, they can form a plane that looks like this. But most oxides have only oxygen in this layer. But if you make a barium oxide, you can get barium in this layer too, because barium 2+, so barium, which always donates 2 electrons in a chemical bond, is the same size as oxygen 2-. So barium 2+ and oxygen 2- can do this, and the net result is a whole bunch of what's called hexagonal perovskites, where you can get something that has like an AbO3 type formula, but involves barium in an oxygen close packed plane, and the net result being triangular lattices. So here's this kid. He's gone on to have his other life. And the first one we made is barium 3 titanium Ru209, which is shown here. In solid state chemistry, you have to prove that you actually made something. So you'll see a lot of these diffraction patterns as time goes on. The crystal structure looks like this. It's got a dimer of basically ruthenium, and then another isolated layer of triangles. So these are all triangles, but this is a dimer. And now when you look at the magnetic susceptibility of this thing, you can see that it has a finite Curie-Weiss theta, 29 Kelvin. So that's good. And ruthenium has unpaired electrons. But the bad news is, as far as I'm concerned, is that this material is a spin glass. And that's because titanium and ruthenium are so similar to each other that we get a measurable amount of disorder, where we have some ruthenium on this site and some titanium on this site. So the net result is we don't have good chemical ordering between the dimers and the isolated octahedra. And the result is, if you have disorder on a magnetic lattice, you can get what's called a spin glass. And although that's interesting to some people, it's not so interesting to me. So the first one we tried didn't work. Then we said, okay, well, if that didn't work, let's try something else. So this one is more interesting to me because instead of having a dimer here, now we have a trimer, meaning we have base sharing octahedra of magnetic atoms separated by non-magnetic atoms. And this trimer is now on a triangular lattice. And the problem for me, the interesting thing for me is, where is the spin on this thing? So, if you have a molecule, like you have a strongly bonded molecule, this molecule has molecular orbitals. So if you can make a trimer like this is starting to look like a molecule inside a three-dimensional magnetic substance. So now you can ask yourself the question, where is the spin here? And that's why I like these trimers. And this is obviously less stable than something where the octahedra do something else, but actually you can manage to get a few of these things to work. The first one we got to work was barium 4, niobium, manganese 3, O12. Now manganese, because of lanthanum manganate, is a famous material, or is a famous ion in oxides. So the fact that we can make a trimer out of manganese was good, but manganese is a 3D element, so you expect the orbitals to be more localized than if the spins were, than if these were 4D or 5D elements. Then you wouldn't be surprised if a local moment picture explains the magnetism of this thing. And it turns out that even though it's in a trimer, which looks like a molecule, some theorists in Russia, Komleva, Komsky, and Streltsov, who are friends of mine, figured out that you can easily explain the magnetism in this substance, and here is its temperature-dependent magnetic susceptibility, by considering local moment pictures for the spins. But this was not enough to deter anything with me, so we made another one, barium 4, niobium, Ru3O12. Now ruthenium is our magnetic element that is based on 4D electrons, so the orbitals are sticking out more. So you expect this thing to be more strongly hybridized than in the manganese case. So in this one, again, you get ordering of the ruthenium here and the niobium in the octahedra here. So niobium 5+ is non-magnetic. So this is now a triangular lattice of cigars. So if you think about this thing, it's a little molecule. You can draw its molecular orbitals, and it has a spin a half in a molecular picture of this thing. And its magnetic susceptibility is starting to look interesting. And now you have barium 4, niobium, Ru3O12. When we look at the magnetic susceptibility as a function of temperature of this one, the intercept of this thing, which is the indication of the strength of the magnetic interactions, is around 150 Kelvin. And it doesn't magnetically order. What? So it did something crazy already. And then when you try to calculate where's the spin, you discover, well, this is broken up. You can have a molecular orbital picture that shows the highest occupied molecular orbital and the lowest unoccupied molecular orbital in the trimer, and you can see that the spins are delocalized in the trimer. Now, the magnetic moment is too low, first of all, for a simple localized picture, and too high for a simple molecular orbital picture. So this one is pretty wacky, and it's got frustrated magnetism, and it's an insulator. Why is it an insulator? If you do a regular DFT calculation and with no electron-electron repulsion, the thing is a metal, but it's not a metal, it's an insulator. So I wonder, is this the definition of a Mott insulator or not? Okay, I wasn't completely happy with that yet, so we moved on to rhodium and iridium. Rhodium and iridium are interesting in these trimers because rhodium and iridium are in the same column of the periodic table. So cobalt, rhodium, and iridium are one column down the periodic table. And now we can look at what is the effect of going from a 3D element to a 4D element to a 5D element as you go, as you put the atoms in the same lattice type. And we put them in the trimers. Now, unfortunately, cobalt, which we all know is interesting from what I showed you before, doesn't work. It makes a perovskite, a cubic perovskite. Now, cubic perovskites were fun for some other reason, but now it just, in this case, I didn't like it. So the competing phase here would be a perovskite, but it's not a perovskite. What we're looking for now is something that has a face-sharing octahedra, show that we get delocalization of the spin in a trimer, and then separation of these from each other by putting a non-magnetic atom in between. And we can do it with rhodium and iridium. We just can't do it with cobalt. But let's see what happens. So something curious happens. So you get magnetism, and you get magnetism with no magnetic ordering. So here is Ba4NbIr3012. Here's Ba4NbRH3012. Now you wouldn't know it, but rhodium is not typically magnetic. And I was, at another meeting with solid state chemist Peter Battle, and he said, you know, Bob, rhodium can be magnetic sometimes. And I didn't actually know that. So this rhodium substance has got a magnetic moment, which is rare but not impossible. I was surprised when I first saw rhodium being magnetic, because you never think of rhodium as being a magnetic element. But this rhodium has this kind of Curie-Weiss susceptibility, which can be fit by the Curie-Weiss law up here at high temperature, where you're supposed to fit it, and it doesn't magnetically order down to 1 Kelvin or 1.8 Kelvin, which is the lowest temperature we can measure something. Same thing for the iridium. I know that iridium can be magnetic a lot of times, so that's all good. So let's see what happens at even lower temperature. So at even lower temperature, you can, it's possible to measure the heat capacity of things. So here's the heat capacity of the niobium iridium 3012 and the niobium rhodium 3012. You can see that the rhodium one seems to magnetically order at around 1.8 Kelvin. So this, the heat capacity is a good way to look at these things, because if you have magnetic ordering, you go from a disordered magnetic state to an ordered magnetic state, and therefore you lose entropy. And so the heat capacity is a good way to look at the entropy loss. And if you see an entropy peak, you see a peak in the susceptibility, that means you lost entropy. So the system magnetically ordered for the rhodium case, but in the iridium case, it didn't. So barium 4 niobium iridium 3012 looks like it's a quantum spin liquid. So the heat capacity continues to rise down to the lowest temperature we can measure it, and that's 0.35 Kelvin. So is the iridium one a quantum spin liquid? I think this is for physicists to tell me. Okay. So thank you for listening. And I think we're good so far. So for me, spins are most dynamic when theory, experiment, and new materials discovery develop in parallel. I think I explained to you, you want to understand what theoretical physicists are thinking about, and then try and make a material that does it, but the material can't be too complicated for others to work on. You want to be able to grow crystals of it. And I realize, of course, that we introduce new materials, that my role in this community is to introduce things to see if experts are interested or not. So maybe some things you think that have the potential to show new physics are amongst these things I showed you today, and maybe there aren't. So, you have to have something. You have to be able to listen to the theorists and see what they're thinking about, then make a material that might do it, and then hopefully grow crystals that are big enough for experimentalists to find new stuff on. So that would be the point here. And if you have an idea that nobody has developed, you're welcome to tell me about it. And it may take 10 years for us to find a material that does it. So you have to be patient with me. But if it's a simple enough concept, then I can get it, and maybe we'll be lucky and get something. Okay, I think that's all. And thank you for listening. I know you're out there somewhere. I think you're out there somewhere.
Thank you very much, Professor Cava. I think if you have given food for thought for many of the theoreticians as you wanted, and I already see Professor Bhaskaran wants to ask some question. Professor Bhaskaran, yeah, please.
Hi, Bob. Thank you very much.
How are you?
I'm fine, great. Very nice talk, very thought-provoking. So I have two short questions.
Okay.
Do you hear me? Okay.
Yeah, I can hear you. I just can't see you. You don't have.
Yeah. Sorry, my video is not working.
Okay.
And so the first question is, the trimer system is very fascinating. It reminds me of organic antiferromagnets, where like ET salts, where the spin-half moments are delocalized. And
Right.
it has very interesting consequences because this Mott insulator will be soft Mott insulator. So most likely under pressure, they may become superconducting.
Wow.
So because many of the ET salts, which are molecular antiferromagnets, two-dimensional triangular lattice materials, under pressure, they create what I call self-doping and undergo superconductivity transition.
Bravo. Yeah, that's a very good connection to make. I hadn't made that connection, but that's a really good one. So do you have people around you who can measure the pressure dependence of anything? Like I think that these, like the rhodium and iridium one in particular, may superconduct at low temperature. That would be fun. So, you know, if I have trouble with high pressure collaborators. My high pressure collaborators have all been in China, and that's a bad thing in the United States nowadays. We're not allowed to work with them anymore. So,
having said that, I just wanted to remark that organic materials are very soft. So the high pressure necessary to create metal insulated transition is very low.
Right. And I always think
the
organic materials are ridiculously interesting, but because they involve organic chemistry, and organic chemists don't care about physical properties of matter, basically, about magnetism and any much. I mean, I guess they do care, obviously, but not about exactly what this community cares about. So, you know, those really interesting materials. So maybe we're somewhere in between there. So yeah, I just have to find a high pressure collaborator who will do it, or it's a good idea, good connection. So
yeah, I will look for some high pressure colleagues.
Yeah, look for
My
somebody.
second brief question is this lanthanum gold antimony system, where you point out that neutral gold atoms form dimers. So
Right.
how strong are these singlets? Are there some magnetic studies? Are they soft singlets? Are they very tightly bound singlets?
That's a good question. I assume they're very soft bound singlets, and there's no magnetic studies. I mean, I don't know what. That's another good point. Like, what do we expect them to do? Are they magnetic or not? And just how strong is the magnetic interaction? This is a little bit tricky to do if you have, but I think it's not impossible at all. So I don't think we ever measured it, or yeah.
Because
So
if the coupling is soft, then there will be some kind of spin gap behavior in susceptibility. Maybe
right.
Right.
That's another good point. So I think we should make that again and measure its magnetic susceptibility. You know, even I always complaining that, you know, people make interesting substances and then don't measure them, but you have a kind of concept for what you think should happen, and then that kind of dictates what kinds of experiments you're going to do. And I didn't think about that aspect of this substance. That's another really good idea. So I think that would be
several other
fun.
questions, but I will ask other. I mean, people,
Thank you.
I'm sure other people are waiting to ask you many questions.
Observations. Okay.
Thank you. Wonderful. Nice seeing you in the two-dimensional world in India.
Yeah. Guys, keep going. Okay. Okay. Well. You have too many ideas. Okay. Well, I'm happy to hear more.
Yeah, I mean, there are questions in messages, like Dhana Sankar has asked some question.
Do I know how to do that? Do I have to
You have to just click on the message.
Okay. Yeah. Some theory papers, blah, blah, blah. Triangular based material. How does this? So how do I? So sodium 2 barium cobalt phosphate is the triangular lattice of cobalt material. I'm trying. I guess I can read the question. Can you comment on Na2BaCoPO42 Committee of Quantum Spin Liquid Physics? Recently, there seems to be some theory papers that discuss the kitty of quantum spin liquid character of this compound. And it gives an archive for it. This is triangular-based material. And how is this honeycomb quantum spin liquid model can be understood there? Well, I don't know. That's a good question. So what did the theorists have some kind of cool explanation? The good news is, from a materials perspective, is that you can grow enough crystals of this material to do neutron scattering on it, so you can actually measure the magnetic interactions. So this is what people are doing right now. So I think that I don't understand the theory well enough to be able to answer your question, but maybe there's another way of doing this Kitaev interactions on a triangular lattice, and that's for the theorists to figure out. But the experimentalists are busy working on that thing right now, so you'll have more data soon enough. Sorry to say. Okay. Sorry, I can't.
Are there any other questions? Sorry, I was muted. I didn't realize. I think he put showcase at thank you. I think Manoranjan has a question. Manoranjan, please go ahead.
Yeah, so sir, I was just wondering about this, the like a material where you have a multiple magnetic plateaus. So what is the structure of that material?
So that's the honeycomb lattice of Cobalt 2+, which is not, Cobalt 2+ is a very interesting element in the periodic table. I think it's low spin Cobalt 2+, which they like spin a half. So it's got one unpaired electron per site. And those plateaus in M versus H have to do with the Cobalt lattice assuming different kinds of magnetically ordered states before you get to the quantum spin liquid state. So you can look back at these old papers from the 70s where people did neutron scattering. There was a French group that was really interested in this substance that has some nice papers from the 70s on the magnetic properties of that substance at low applied fields. Now, basically, if you ask the question, how can a magnetic field remove the ordering in ruthenium trichloride and barium cobalt arsenates, I think that's kind of a cool question, where I think that the magnetic field increases the ferromagnetic term to the Hamiltonian, and so these things, which might be dominated by antiferromagnetism, you can adjust the ferromagnetic to antiferromagnetic interactions by putting a magnetic field on them. So the magnetic field enhances the ferromagnetic part. So I think that's the logic behind why that works. And before you cross to a full ferromagnetic state, which I presume happens at high temperature, you get this quantum spin liquid state in between. Okay.
Okay,
I don't know what
thank you. Thank you.
I think there is a question in the chat box and a couple of hands raised. The question the question in the chat box is from Achinta Low, who wants to know how the magnetic field can make ruthenium trichloride and barium cobalt arsenic compound quantum spin liquid. I mean, basically, I think he wants to understand what is the influence of the magnetic field.
Basically, I think that it just makes a difference what direction you put the magnetic field on. And I think the theorists have, or the experimental physicists have understood this. And basically, that's by changing, I showed that diagram of how you get a balance between the different kinds of first and second nearest neighbor interactions on a honeycomb lattice. It gives you different kinds of magnetic ordering. And there are certain ratios of those things and that are intrinsic to the material itself by the way the spins are coupled. And then you can adjust the ferromagnetic component by putting a magnetic field on it, and you can cycle through the different kinds of magnetically ordered states by putting a magnetic field on it. And a magnetic field favors ferromagnetism. It tries to line spins up. That's how that works. Okay, and that's But that's the good news is that they work field range where you can actually see it.
I hope this answers his question. And Tirupati Shetty wants to, Professor Shetty, can you please go ahead?
Yeah. Professor Cava, thank you for the nice talk. I have a general question. So what motivates you? You have produced lots of very new brand new crystals. So the motivation behind is physics or chemistry to make lots of new crystals.
So I can, your question is breaking up, but I think you asked, what did you ask? Like a
Shall I repeat the question? Maybe if I'm audible clear now. So, I mean, you had made lots of new crystals. So I just want to know the motivation behind that. Is it physics or chemistry?
Right. So for the most part, obviously I'm a solid state chemist. So I live in a culture where chemists are not frightened by biology. So biology is okay. So finding new molecules that have biological activity is something that chemists don't mind doing. But physicists are scary human beings, or can be scary to chemists, and not to me. And so the trick would be to listen to what's on people's minds and then do your best to find something that will illustrate what they're thinking about. I think for me, theoretical physics are fun because they have all sorts of ideas that are unfulfilled thoughts about how the world should work. And some of those ideas are going to be right. So, why not try to make something that does that and not be scared by physics? So that's basically the story here. And listen to theoretical physicists, find out what they're thinking about, and then try and make something that does it. And maybe it will, maybe it won't. So if it doesn't, at least you tried. They're going to be mad at you, but it doesn't matter.
Okay. So then when you start to make new crystals, so what are the chemistry of the elements that you actually consider important?
Right. So I think for me, for magnetism, obviously unpaired electrons are important. So I think that was a very good comment about gold. Maybe you can find magnetism where you don't expect it, but the 3D elements are the most interesting to me because they have electrons that you expect to be in orbitals where they're unpaired. Now, for a lot of chemistry, you end up with D8 or D6 electron configurations, which for me are particularly boring because they're not magnetic, but we typically magnetic. But sometimes you can get magnetic ones anyway. And, I think for me, the transition elements, which most people try to avoid in chemistry, are the interesting ones. But there are interesting and wonderful cases where you get magnetism where you don't expect it, which I think is a good thing. So, yeah, if you're going to concentrate somewhere, I would concentrate on transition elements and things. Well, for my generation anyway, things that are not explainable by simple pictures. But maybe your generation is different. Okay. Yeah.
Okay, and here the dimension, like the diameter of the elements or this kind of thing, doesn't matter at all to while making a new material, something like that.
No, I think it's just like what orbitals does the electron occupy? So I don't care if it's yeah. For me, it doesn't mean the lattice type has to be simple for a solid state chemist and interesting for a physicist. So it can't be too complicated. I have failed in the past to get the community excited about things that I thought were interesting because the crystal structure was too complicated. So,
Okay, I think we move to two more hands raised.
Thank you for that.
Yeah.
A nice question about spin glasses. So spin glasses typically happen when there's chemical disorder, but you can also, I think there are some cases known where you get spin glass behavior where the amount of chemical disorder is really, really low. So there are certain systems that are right at the borderline between magnetic ordering and not, where you can get spin glass behavior when you have only a small amount of disorder. And I think, oh, you don't want detectable. Yeah, this is an interesting question because spin glass behavior typically happens when you have magnetic disorder because it has to do with the fact that you have different strengths of magnetic interactions that give you magnetic ordering at different effective temperatures for different pairs of magnetic atoms. So, I think in my mind, disorder is bad. In some minds, disorder is good. So, as far as I know, spin glass behavior only arises through the disorder. You can have magnetic frustration, and maybe maybe triangular lattices have different kinds of coupling that can lead to disorder, lead to spin glass behavior, but that's relatively rare. I think a good example of that would be strontium gallium chromate SCGO, which has a Kagame lattice that has a lot of magnetic disorder in it, and it's also a spin glass at low temperature. So this is a good question. Another good question. Okay.
Thank you. Yeah, Shuhasini Loud, there's a hand raised. Do you want to ask question?
No.
Yes.
Okay. Thank you.
Hello. Yeah. So sorry.
Yeah.
Can I ask a question? Yeah.
Yeah, I think you can try.
Okay. So actually, thank you, sir. I enjoyed your talk a lot, and it's very informative for me to listen to you. My question was basically, I mean, you talked about the Kitaev model in the earlier part of your talk. And I mean, so there are materials like lutetium Fe2O4, for example, which is a layered honeycomb structure of charge ordered array of Fe2 plus and Fe3 plus ions on a honeycomb. Now, what people have basically done is they have done some theory on it and basically determined that the orbital superexchange, not the magnetic superexchange, but the orbital superexchange, has a form which is exactly like that of a Kitaev model.
Right.
So this is a Kitaev model in the orbital sector, not in the spin sector.
That's a good idea. So basically, the spin contribution to the magnetic moment is 0 because it's D6, and then you have just an orbital contribution that makes a Kitaev kind of model.
Yeah, so the point is, I mean, basically much more than spins, the orbitals are very sensitive to structural distortion effects. So,
right.
So it might well happen that the analog of the spin liquid, which would be an orbital liquid, would be basically become unstable via structural distortion to some kind of dimerization.
Right. That's another beautiful observation. Okay, so that might be interesting. The thing, I have kind of ignored that family of compounds because I assume there's disorder, but are the iron 2 plus and iron 3 plus actually ordered in that substance? That you said that.
Yeah.
So I know that there's been a lot of noise about things with a similar structure type, but I assume that they have disorder, and so they're basically spin glasses. Like, I know there was a lot of noise about ytterbium, magnesium, gallium O4, which is something different, same crystal structure, but in that case, a disordered array of magnesium 2 plus and gallium 3 plus. You say for the iron one, they're ordered.
Yeah.
So that's interesting. So I wonder if that, I don't know. So basically, it kind of depends on whether the community is convinced that that is a good system or not. So that's a really good idea. So why not an orbital ordering or an orbital interaction, like an orbital liquid?
Yeah.
Yeah, I haven't worked on it. Okay, good observation too. I have to take notes on all these.
Yeah, so I mean, in that case, how would one do it? I mean, would one go to a resonant X-ray scattering experiment, or how would one basically tease out
I think
the orbital?
it's more subtle, right? Because basically you're asking for a probe that um, probes orbital. You want a probe that probes the orbital contribution to the magnetic moment, or the orbital occupancy, the
Yeah,
orbital occupancy.
yeah.
And I
So,
think,
something like analog of the structure factor.
right, so it's a structural system. So you'd have to say that there's no preferred orbital occupancy, which
Yeah.
you have. I think it's kind of a subtle thing. I think, have you talked to Paul Atfield in Edinburgh about this? Because that's kind of like up his alley. He's the one who figured out the magnetic ordering for the Verway transition in FE 304, I think. So maybe this kind of thing is something that he could do. Yeah, I think it's a subtle. It's a bit too subtle, but it's a good point.
I think there is a question from Professor Priya Mahadevan. Can you please ask the question?
Yeah, can you hear me?
Yes, I hear you.
Okay, so I had just, it was a very nice talk. I just had one rather naive question, which is that it's always among the 3D, it's always the cobalt, which seems to have a very large orbital moment in various compounds. And it's
Right.
not as if its spin orbit interaction is substantially different from the others. So I was just curious, why is it so much enhanced? Do you have any thoughts on that?
That's a question. So why is an interesting question. And one part of your statement is why do you think it's not an anomaly? Like why are you saying that the spin orbit coupling is the same as the other transition?
It's not exactly the same, but I mean maybe 10 MeV, 20 M. I mean it's just a factor of few tens of MeV different, probably from the manganese, for instance.
Right. So you would say that the spin orbit coupling for cobalt is not anomalously large. So cobalt 2 plus, there's, no matter how you count it, if I remember correctly, no matter how you count it, even if you say there's 3 unpaired electrons on cobalt all the time, the spin only contribution is still not big enough to get you there. So there are, I don't know why, but basically there are people who can actually count the orbital occupancy. They can look at what orbital is occupied for cobalt, and they come out to be a low, the cobalt comes out to be a low spin state. So where did all that magnetic angular momentum come from, if not from the orbital? You have another explanation? So
Yeah.
this comment that you make about the spin orbit coupling not being strong for cobalt or not being anomalous for cobalt, is that based on what? That's based on some calculation or what?
That's true. From atomic Hartree-Fock, for instance, that's the usual starting point usually for various calculations of the X and CD spectra.
Right. So I wish somebody could answer that question. Like, why is cobalt anomalous? No matter how you cut it, the observation is bizarre. So if your question is why, then everything about cobalt is anomalous. There's no way to explain it. So in my brain, no matter what if you ignore the spectroscopy that says that it's low spin cobalt, what happened? Even if it's cobalt, even if it's high spin cobalt, it's still not enough. So where did that moment come from? Okay. Anyway, I just always assume it's high spin orbit coupling, but maybe it's not. Maybe it's some other factor that nobody knows.
Or could it be that it's sitting at a wrong lattice site which contributes enormously? Would that make such a huge difference? An interstitial site, for instance?
I mean, like the cobalt content is wrong? No, I don't think
Yeah.
that's it.
Okay.
I mean, it just happens all the time. So
Right.
everything has to have something wrong with it. So you need a close packed lattice where you have a lot of extra cobalt in there.
Right. Yeah.
I just
Exactly.
think it would be easily observed and you just don't see it. Okay, thank you for the question.
Okay, thank you.
Okay, thank you. I have two small questions. One is on your trimer compound, which is the barium 4, niobium, ruthenium 3O12. Even the 113 compound, namely the barium ruthenium O3, that has different polymorphs, as you very well
Right.
know.
I
And
worked on
there are some of the polymorphs has this trimer. So do you expect a very similar kind of behavior also there?
Well, that's a good question. So those barium ruthenate polymorphs, unfortunately or fortunately, the dimers and the tetramers or whatever is in there are connected to each other. Here they're separated. So those things are a mixture of regular perovskite packing, cubic perovskite packing, and hexagonal perovskite packing. So they're too strongly coupled. And I remember that back many, many years ago, we saw some bizarre differences between these polymorphs, and we never could get to low enough temperature to make a difference. So that's an interesting point to look at those again.
And the other small question is about the first part of your talk, where you have the rare earth pyrochlore, you also had the 3D pyrochlore. Of course, the rare earth goes to the A site and the 3D cation goes to the B side. I mean, of course, you saw frustration effect on both, but which one is dominant? Of course, there is a geometric frustration. There is also an electronic frustration possible.
So I always think of those things as they're insulators. So they're geometric magnetic frustration. So the electronic contributions to the magnetic interactions must be small. So I think that one in intermetallic compounds, you can have electronic terms, but in these things, because they're insulating, I think you don't. Okay, thank you for accepting that answer. I think that's the right answer. Okay.
Okay, thank you so much. I don't see any hand raised or any other question in the chat box. So thank you so much. And as you can understand, your talk has generated tremendous amount of interest. So we have answered the last sentence of your abstract. And I do think there will be a lot of collaboration opening up, in the sense I'm sure people can write email to you if they're interested specifically on some specific compound. And thank you once again for a very, very brilliant talk and a very nice exposition to a set of compounds. Very interesting.
Thank you for having me. And I think, thank you for being interested in some of these materials. Bravo. And there are lots of good points.
Manoranjan, you might want to add some closing remarks.
Okay, so certainly I should start thanking you for sharing the colloquium, and I thank Professor Cava for excellent and thought-provoking talk. Also, and it's very important that he has such a busy schedule, but still he agreed to give this talk in such a short notice. And thank you very much, sir, and for this.
Yeah, you're welcome. And I hope I wasn't too sleepy. Okay, thanks everybody.
No, thank you. No, it's a so early morning talk for you. It might be very difficult. Yeah. Okay, thank you very much.
Thank you very much.
Thank you so much.
Thank you.
You're welcome. Good luck.
Okay. So we close this session. Thank you.